everyone, welcome back. Today we're going to be looking at probability in chapter 11, and we're going to talk about the difference between empirical and theoretical probabilities. The first part of the notes, you can read through the history and also some definitions, such as what an experiment is, what are outcomes, what's meant by the word event, and also how it relates to probability, which is just a number that measures the likelihood that an event will occur. And we symbolize that using P and E, and it just means the probability of the event. The two types of probability we're going to look at are empirical and theoretical. So empirical basically deals with experiments. When you can look at actual observations. So if you take dice and you roll it and you record how many times a 1 comes up or a 6 comes up, that's empirical probability. Theoretical probability is determining the chance of something happening in the future by observing past results. So an example of theoretical is if we were to roll a 6-sided fair die, and I want to know what's the probability of rolling a 6. You don't physically have a die to roll, but we know that there's 6 sides on a die, and there's only one 6. So if I want to find the probability, I would just take the number of outcomes favorable, so how many 6s are there, and divide that by the total number of possible outcomes. There's 6 faces. So there's 1 6 and there's 6 faces. So the probability of rolling a 6 would be a 1 over 6. Now, if you were to roll a die, you wouldn't necessarily get a 6 the first time. In fact, it may take a large number of times to obtain a 6. But in the long term, if you were to increase your sample size and you were to roll the dice a large number of times, you would get close to 1/6. And that's referred to as the law of large numbers, which states that the probability statements apply in practice to a large number of trials. Okay, let's look at some examples. So we talked about empirical probability, and at a Little League concession stand, the last 40 beverage purchases were as follows: 16 bottles of water, 14 bottles of sports drink, and 10 bottles of soda. Using this information, determine the empirical probability that the next beverage purchased is a bottle of water. So if I want to find empirical probability, you can refer back to the notes. The probability of the event is just how many times this occurs over how many times it was performed. So if I want to find the probability that the next purchase is going to be water, there were 16 water bottles, and how many experiments were performed? Well, there were 16 bottles of water that were sold, 14 bottles of sports drink, and 10 bottles of soda. So I'm going to add 16 plus 14 plus 10, which gives me 40. So the number of times bottles of water were sold was 16 over a total of 40 sales. So the probability is 16 over 40. We always want to reduce. So if I reduce 16 over 40, 8 goes into 16 2 times, and 8 goes into 45 times. So the probability is 2/5. You can also change the fraction to a decimal by dividing. 2 divided by 5, you would get 0.4. So that's also an acceptable answer. If I want the probability that someone is going to buy a sports drink, there were 14 bottles of sports drinks sold out of 40. So the probability is 14 over 40. And both numbers are divisible by 2. 14 divided by 2 is 7. 40 divided by 2 is 20. So the probability is 7/20. And the probability that the next beverage purchased will be soda will be 10 over 40. So soda. And 10 over 40 reduces to 1/4. We're going to do the same thing, except now we have a table. And a pharmaceutical company is testing a drug that's supposed to help reduce high blood pressure. The drug is given to 500 individuals with the following outcomes. So 379 people had blood pressure that was reduced. 62 of those people had blood pressure that didn't change. And 59 people actually had blood pressure that was increased. If the drug is given to an individual, determine the empirical probability that the person's blood pressure is A, reduced, B, unchanged, and C, increased. And this time we're going to write our answer as a decimal. So again, empirical probability, I want to find the probability of the event, how many times it occurs over the number of times this experiment was performed. So if I'm looking for letter A, I have 379 over how many times this experiment was performed. So feel free to pause the video and try to figure out what the denominator would be, and then unpause when you're ready. If I add 379 plus 62 plus 59, I get 500. And they tell us in the problem, the drug is given to 500 individuals. So if you were to add those, since it was an experiment, there were 500 people that were given that drug. So 379 divided by 500 is 0.758. So the probability, if I was to look at this as a percentage, all I would have to do is move the decimal to the right 2 places, and this would be 75.8%. So in other words, out of the 500 individuals, 75.8%, or almost 3/4 of those people, had blood pressure that was reduced. Now, it doesn't say to change to a percent, but I wanted to show you that 0.758 is really 75.8%. Okay, pause the video and see if you can figure out the probability for the unchanged and the increased, and then unpause when you're ready. So letter B, we want to know the probability a person's blood pressure is unchanged. So that's going to be 62 over 500. And if I divide 62 divided by 500, I get 0.124. And then in letter C, I need to find the probability that it's increasing. And that's going to be 59 over 500, which is 0.118. When you get a chance, take a look at the link that I provided and play around with the sliders to look at what the law of large numbers has to do with theoretical probability. There's some important facts that you want to make sure you're aware of with probability. So the probability of an event that will never occur is 0. The opposite of that would be the probability of an event that's certain to occur, and that's 1. Probability will always be between 0 and 1 inclusive. So you're never going to have a probability that's negative, and you can't have a probability greater than 1. The sum of the probabilities of all possible outcomes of an experiment is 1. So if I go back and look at that last example we did, and I added up all of those probabilities, 0.758 plus 0.124 plus 0.118, I would get 1. It will always add up to 1 or 100%. But I'm going to put a red flag next to number 3. if you ever get a probability greater than 1 or less than 0, it's wrong. Your probability always has to be between 0 and 1 inclusive. Okay, let's look at an example of theoretical probability. A fair die is rolled. Determine the following. Okay, let's talk about if we have a die, how many faces does it have? A fair die has 6 faces, and they're all equally likely to occur. So that just means that if I roll a die, I have the same chance of rolling a 1 as I do a 2 or a 3, and so on. So if we think of this as a set, if you roll a die, the possible outcomes are 1, 2, 3, 4, 5, and 6. So what's the probability of rolling a 2? Okay, so we're assuming now that we're looking at theoretical probability. So theoretical is just the number of outcomes favorable to the experiment or the event over the total number of possible outcomes. So to find this, I need to know how many 2s there are. There's 1, 2. That's the number favorable over the total possible. There's 6 sides. So my probability of rolling a 2 is 1/6. Next, I'm asked for the probability of rolling an even number. So my even numbers are 2, 4, 6, 8, 10, and so on. So if I'm looking at a die, my even numbers are 2, 4, and 6. That's 3 numbers out of 6. And 3/6, again, you always want to reduce your fractions. 3/6 reduces to 1/2. What's the probability of rolling a number greater than 3? Greater than 3 means we don't include 3. So there's only 3 numbers greater than 3 on a die. It would be 4, 5, and 6. So the probability, again, is 3/6 or 1/2. Pause the video and try answering the next 3 questions, and then unpause when you're ready. So the first question asks, what's the probability of rolling a 7? So if you'll recall, that would be the probability of an event that cannot occur is 0. You can't roll a 7. The highest number is a 6. So the probability is 0. It's never going to happen. What's the probability of rolling a number less than 7? Less than 7 means you don't include 7. All of the numbers on the die are less than 7. So that would be the second fact of probability. The event that's certain to occur is 1. So we know that all of the numbers, there's 6 numbers out of 6 possibilities, and 6 divided by 6 is 1. If you didn't know what a prime number is, hopefully you looked it up, but it's a number that is divisible by itself and 1. Some examples of prime numbers: 2, because 2 times 1 is 2. 3 times 1 is 3. 4 is not prime because in addition to multiplying 4 times 1 to get 4, it also has factors 2 times 2. 5 is the next prime. 6 is not prime because 6 is 6 times 1 and 2 times 3. 7 is prime. 11 is prime, 13 is prime, and so on. So they're numbers that are only divisible by themselves and 1. So on a die, we're only looking at 2, 3, and 5. So that's 3 numbers out of 6,
The mail has arrived.
and 3/6 is 1/2. In any experiment, whenever we perform an experiment in probability, you only have 2 options. Either the event is going to occur or it's not going to occur. So for example, either it's going to rain today or it's not going to rain today. I know that that's certain. That is going to equal 1. I am 100% certain either it's going to rain today or it's not going to. So what we want to remember about probability is the probability of an event A plus the probability of it not occurring is always going to equal 1. And you can take that formula and kind of move things around. If I want to solve for the probability of not A, if I take my formula and go back to algebra 1, I'm solving for this, so I'm going to subtract this from both sides. And I would get the probability of not A is equal to 1 minus the probability of A. So that's another version. Both of these are the exact same thing, just written slightly differently. So if you ever want to find the probability of not, always just do 1 minus the probability that it is occurring. One of the things that they're going to use a lot in this chapter are card problems. And the book always assumes that everybody knows how to play cards and everything there is to know about cards, but that's not true. Especially in certain cultures, people aren't introduced to cards, so it's kind of unfair to ask card questions. So for this example, I made sure to include a diagram, but also information about cards if you've never played. Excuse me. So every deck of cards has 52 playing cards. That's for a standard deck, and that does not include the Joker cards. Okay, we don't include those. The deck consists of what's called 4 suits: hearts, clubs, diamonds, and spades. Every suit has 13 cards, including the numbered cards. So we consider an ace a 1, and then through the number 10. And then there's 3 face cards. There's the jack, the king, and the queen. Something else that's important to remember: hearts and diamonds are your red cards, and clubs and spades are the black cards. There are 12 face cards. So how are they getting that? Well, every suit has 3 face cards: the jack, the queen, and the king. There's the jack of hearts, the queen of hearts, and the king of hearts. And then there's the jack of diamonds, the king of diamonds, and the queen of diamonds. And the same thing for the clubs and spades. So that ends up being 12 face cards. And you end up with then 4 jacks: the 4 of hearts, the 4 of clubs, the 4 of diamonds, the 4 of spades, or jack of hearts, jack of clubs, jack of diamonds, jack of spades. And then the queen of hearts, the queen of clubs, the queen of diamonds, and the queen of spades. And then the king of hearts, king of clubs, king of diamonds, king of spades. So all of that information there is important to know about cards. We're going to see a lot of card problems, and you can always refer back to this if you need help answering the question. Let's say we have a standard deck of playing cards, so 52 cards, and we draw a card from the deck randomly. So we don't know which card we are going to be picking. It's random, so it has an equal likely chance. All right, so what's the probability of drawing an 8? So what we have to remember is, again, there's 4 suits, and every one of them has an 8. So if you look at the diagram here, all of these are 8s. There's 4 of them. How many cards are there? There's 52. So the probability of drawing an 8 would be 4 out of 52, which I can reduce. 4 goes into itself once, and it goes into 52 13 times. So the probability is 1/13. Now, what if I ask you, what's the probability of not choosing an 8? So if you'll remember, we have this formula up here. The probability of not choosing an 8 would be 1 minus the probability of choosing an 8, which we found right here. So all I'm going to do is just do 1 minus 1/13. And if you'll remember, you need to have the same denominator to subtract. So we're just going to turn 1 into 13 over 13. And when I subtract 13 over 13 minus 1 over 13, I get 12 over 13. So the probability of not drawing an 8 would be 12 over 13. What's the probability of choosing a face card? Okay, so recall your face cards would be your jack, your king, and your queen. Now remember, you've got a jack, king, and queen, and I'm highlighting them in the picture in each of the suits. So how many are there? There's 12 because there's 3 face cards times 4 suits. So that means there's 12 cards that are face cards out of 52. And 12 out of 52, 3 goes into 12, or 4 goes into 12 3 times, and 4 goes into 52 13 times. So the probability is 3 over 13. Okay, you can pause the video and now try these last 3 on your own, and then unpause when you're ready. Okay, so now I'm looking for the probability of choosing a club. So if you recall, a club is a suit, right? And there are 13 cards in each suit. So to get a club, here's your clubs right here. It's all these cards right there. There's 13. You can count them. So the probability is 13 over 52, which reduces to 1/4. The probability that you're going to draw a heart and a spade. So we're only drawing one card. It's impossible to draw a heart and a spade since we're drawing one card at a time. So the probability there is 0. Remember, and implies both. And then the last question is the probability a card greater than 5 and less than 9. Okay, greater than 5 means it can't include 5, so the first number we would start at is 6. And it's got to be less than 9. Remember, and means both. So less than 9 means you can't include 9. So we're only looking at the 3 numbers 6, 7, and 8. How many 6, 7, and 8s are there? Well, remember, every suit has a 6, 7, and 8. There's the hearts, the diamonds, the clubs, and the spades. So that's 3 times 4, that's 12 different cards out of 52. And if we reduce that, 12 over 52 equals 3 over 13. That is the end of 11.1. I hope you enjoyed. Please go back and reread the definitions and the history of probability, and then we'll continue with 11.2, which talks about odds.